Let's continue talking about the three reactions that the three reaction mechanisms in the substitution of aromatic compounds. So we have talked about that, and let's remember the type of intermediate. The intermediate here is called a sigma complex, and it's not aromatic. And here the nucleophile is the pi electrons in the ring. That's one structure. You have several resonance structure, but that's called a sigma complex. And we can say, let's do like a general after resonance. We can do, the charge can be delocalized. So we're going to have delta positive ortho here, para, and ortho here again. It's delta positive because, again, your electrophile is something that is electron deficient, so I represent it that way. In the case of the substitution, nucleophilic substitution at aromatic compounds, you have a nucleophile. And in the example that I did in the other video, I had an OH, but let's say that I have a general nucleophile here. Choose any. Nucleophile, strong nucleophile. So my intermediate, it is the attack of the nucleophile at an aromatic ring that must have a good leaving group here, and halide, for example. So I'm going to put an X, and I'm going to have that attack, but I also need an electron withdrawing group, ortho, here, or para to the leaving group. And the attack happens at the carbon that has the leaving group. So here, when you do that, you form the following intermediate. The intermediate this time will have a negative charge. And now you have here, say, nucleophile had a negative charge, X, my leaving group, and I have an electron withdrawing group. And as you see, the electron withdrawing group is, in this example, para to the leaving group. We can, doing resonance, the charge is delocalized, even though this compound, the intermediate, is not aromatic, but you can delocalize the charge, and I'm going to draw this, say, the structure of the intermediate, in which here you have an sp3 carbon. That's your electron withdrawing group. And you will have partial negative here, partial negative, and partial negative. And because of the nature of that intermediate being negatively charged, it is important to have an electron withdrawing group here to help stabilize. So notice similar here, the sigma complex is, has a positive charge in all those places. In, say, ortho, where the place you put the electrophile. Ortho in para, and here you have the nucleophile has a negative charge. To say your Mesenheimer complex is then not aromatic, similar to a sigma complex, but then the charge is different. Mesenheimer. And so the last mechanism doesn't go that way. It goes in two steps, but this time we're going to be doing elimination-addition. So now I'm going to just erase part of that because I need room to draw the last mechanism. So now we know how is that, and I'm just going to leave what is required. So some reactions, if you don't have an electron withdrawing group, some reactions, these reactions can happen, but at extremely strong conditions. Say, if you have a substrate, the third mechanism. Say that you have chlorine, so chlorobenzene, and this reaction I want to do, let's attack with a nucleophile, but here you need very high temperatures. So this reaction does not need a electron withdrawing group, but you do need a nucleophile. So you need a nucleophile, strong nucleophile, or high temperature. So strong nucleophile, for example, the amide anion, or you can use OH, but if it is so, you need higher temperatures. Here you don't. So, but you don't need the electron withdrawing group, but you can identify what's going on because this reaction will happen in the absence of electron withdrawing group. But again, need a stronger reaction condition. The net, say, result here, your product is phenol, but it cannot be by the mechanism that we drew on the nucleophilic substitution. It doesn't happen that way. And there's evidence to that. So if I say that I labeled this carbon, well, no, let me do things a bit different. Let's just do that for now. The mechanism that's proposed for that is the following. So I'm going to start again with my chlorobenzene. And I'm going to put an H here, one of the H's. So under very strong conditions, these are strong base, strong nucleophile. So you will have, say that I have now amide. So you're first going to have a proton transfer reaction, removing that, and these electrons are going to form the following movement to form an intermediate that the name is Benzyne intermediate. So here you have, notice, proton transfer, removing that, you form the triple bond in loss of leaving groups. So two things happening at the same time, proton transfer and loss of leaving group. Once that you form the benzyne intermediate, that's the step, the elimination step in the mechanism. The second step is the addition. So now I'm going to erase that part and say, this is a step one. This here, step one. Now from the benzyne, I'm going to draw the step two. Starting with benzyne. So it is an alkyne, right? And then here, what you're going to have is saying you have the amide. So amide anion here acting as a base, and here it will act as a nucleophile. So you will have a nucleophilic attack here and create the following. Now you're going to have an H2, and here you will have this species anion, so with the negative charge here. And that can abstract, say that you do that reaction in ammonia, and it can anion abstract one hydrogen here. And the end result is that you had substituted, I'm going to draw it here better. We have substituted the aromatic ring and have installed an amino group. So it had happened then in two steps. First step was the elimination. We have eliminated the hydrogens, so strong base, strong nucleophile. Remove that, you form the benzyne intermediate, and step two, once you have the intermediate, this species now acting as a nucleophile, attacking here and forming that intermediate. Step three, you have a proton transfer to have the final product. So these are the mechanisms. And again, when we are doing problems, we need to identify what we have. What is a reagent? Is a reagent an electrophile or a nucleophile? Once you have established that, if it is an electrophile, we're going this way. And then there are electronic effects that we need to study to be able to predict products. We're going to go in that in problem. And then if you have a nucleophile in your region, you have either these two mechanisms. For the substitution SN-AR mechanism, you need to have a leaving group and electron withdrawing group. In the next, if you don't have an electron withdrawing group, ortho-pair that mechanism to the leaving group, this mechanism doesn't occur. You can have this reaction in the absence of electron withdrawing group, but you still need your leaving group. You need a leaving group, and that's in a strong nucleophile. You need this too. And that is stronger conditions. So now we're going to start doing problems. But again, that's the analysis that you will do when you're doing problems. See what you have, what is your region, and what is the structure of the molecule that you are doing.